Hello everyone, we are Team 21047, the Ventilator Improvement System team. This project is sponsored by Dr. Marvin Slepian and mentored by Steve Larimore. Now with the team members.
Hi, my name is Casey Broker. I'm a mechanical engineer and the team lead.
I am Mohammed Al Yusuf. I am the electrical engineer.
I am Abdulaziz Bawazir. I am the industrial engineer.
I'm Amanda Heald and I'm a biomedical engineer.
I'm Marco Jacob and I'm a computer engineer and the procurement lead.
Hi, I'm Shivangi Awasti and I am the other biomedical engineer on the team.
The goal of this project is to improve the performance of current low-cost ventilators by designing a mechanical ventilator from readily available materials and implementing an advanced control system to monitor clinical data.
With the COVID-19 pandemic on the rise in early 2020, healthcare and medical facilities become overrun with ever-increasing amount of patients who demand ventilator support. Due to extreme costs of sophisticated mechanical ventilators, these facilities could not keep up with the spread. Thus, Team 21047 was called upon for innovative solution as makeshift low-cost ventilators were being designed by engineers around the world. They did not quite meet the demand to compete COVID-19. A mechanical two-arm and gear mechanism was modeled in SolidWorks for analysis and was fabricated as the external compression system for the ventilator. A kickball was reinvented into a reservoir for air and oxygen supply to the patient in place of an ambu bag. An advanced control system was also implemented to monitor airflow, pressure, oxygen concentration, and inspiratory-expiratory ratio to the patient during the breathing cycle. These clinical parameters can all be monitored and controlled by a potentiometer knobs within the control system where values are read on the LCD screen.
Due to the increasing demand for ventilators, it was imperative that this design considered rapid prototyping and fabrication through the use of inexpensive, readily available materials. The final mechanical design consists of a two-arm, gear-driven compression system that triggers the airflow from the air reservoir to the patient via the breathing circuit. Here's how it works. Two mechanical arms with an embedded gear are interlocked and supported by two plates and bolts. One of the arms is also interlocked with the pinion gear on the motor, the driving force of the mechanism. When the ventilation program is turned on, the arms are in the outward or decompressed position. The motor pinion turns counterclockwise to simultaneously move both arms toward the center to compress the air reservoir and send it to the patient. The motor pinion then rotates clockwise to decompress the reservoir and move the arms outward for the next cycle. This process automates what is known as manual resuscitation, which satisfies the requirements of producing a low-cost and rapidly manufactured device.
Next, we have the breathing circuit subassembly for our mechanical ventilator system. The airbag, which is the kickball, tubes, the humidifier, and the decontamination chamber are all of the components that make up the breathing circuit subsystem. Since most current emergency ventilator designs require the use of an ambu bag as a mode of air delivery, our team considered using household products such as a kickball as the main positive pressure chamber, which is one of the most innovative aspects of our style. This demonstrates that we can make use of anything that is easily accessible and that can be pressurized. The air circulates through the chamber and out to the patient through an external compression. The kickball will provide an inlet and outlet such that airflow tubing can be attached. This provides strong sealing and avoids any air escaping. Therefore, this airtight seal system is strong and long-lasting. We also developed and 3D printed our own check valve and purchased HEPA filters because our concept did not have an ambu bag with built-in air check valves and filters. So this allowed us to provide a steady flow of filtered air to the patient. Furthermore, we noticed that current designs failed to consider air temperature during inhalation, so we implemented a humidifier in order to add moisture and warmth to the air that is delivered to the patient as they're inhaling.
The air exhaled from the patient then travels to the decontamination chamber. The patient has likely exhaled viral particles, so the air needs to be filtered before being released into the atmosphere. The decontamination chamber is designed with two medical-grade HEPA filters, one at the inlet and one at the outlet, and a chamber with the UVC light. The HEPA filters and the UVC light filter and destroy viral particles respectively. Although this is not a cure for COVID, it does provide a means of slowing the spread of the virus from the patient to the medical personnel. To conclude, as the kickball reservoir is compressed, air is released and travels through a pipe towards the patient. It first travels through the humidifier, which adjusts the temperature of the air, and then gets inhaled. After being exhaled, the air then travels through another pipe to the decontamination chamber. It goes through the medical-grade HEPA filter, and then through the chamber with the UVC light. At the outlet of this chamber is another HEPA filter. This process ensures the high quality of the inhaled air as well as the filtration of the exhaled air.
The electrical and computer subsystems consist of an Arduino Mega, an LCD screen, potentiometers, oxygen and pressure sensor, buzzer for the alarm, motor controller, gear monitor, and finally a 500 watts power supply. We use the power supply to power up the Arduino with the required 5 volts, and the motor controller with the required 12 volts. We use the motor controller to supply our gear motor with the necessary 12 volts. Our mechanical arms are driven by our 12 volts gear motor. To control the motor, we use the RoboClo motor controller. This allowed us to control various features of the motor such as acceleration, deceleration, distance, speed, current sense, voltage limits, and more.
We have a total of 3 potentiometers, each programmed to control different aspects of the system. Respiratory rate, IE ratio, and tidal volume are all controlled respectively through our potentiometers and Arduino. Additionally, our LCD screen will display real-time updates of pressure and oxygen levels provided by our pressure and oxygen sensors. Lastly, an alarm will be triggered for irregular breathing, loss of pressure, or any power fluctuation in the system.
Our ventilator uses 2 separate printed circuit boards. The top circuit is used for potentiometers, LCD screen, pressure sensor, and our alarm system. The bottom circuit board is used only by our oxygen sensor. We needed to fabricate a separate PCB because our voltage supplied to our oxygen sensor is substantially lower than the voltage supplied to the rest of the components. Our circuit boards were designed using Eagle software and fabricated by JLC PCB Fabrication.
For the requirement verification, we performed acceptance tests for safety, emergency shutoff, regulation, electrical, and the user interface. Here is the approximate timeline we followed to complete our acceptance tests. For the safety ATP, we tested the alarm sounds produced when respiratory parameters go out of range. For the emergency shutoff ATP, we tested to make sure that the ventilation system turns off when the emergency button is pressed. That is, power no longer gets supplied to the system. For regulation, we tested to make sure that the temperature of the air being supplied was 98.6 plus or minus 1 degree Fahrenheit. We also tested the air quality index of the exhaled air to make sure that the decontamination chamber was filtering it properly. As discussed previously for the electrical ATPs, we tested the pressure and oxygen sensors. For the user interface ATP, we tested that the display, interface modification upon adjusting parameters using the rotatable knobs, and the GUI alarms were working. We recorded the results from each of our acceptance tests in datasheets like this one. The one displayed is for our user interface test. Here's a video of our overall system in action. Overall, our ventilator provides positive pressure ventilation of a blend of medical air and oxygen, includes a user-friendly interface that displays clinical information and system parameters, and decontaminates expired air. It is made from readily available materials and is portable, meeting the requirements of our sponsor.
Throughout this project, Team 21047 has overcome many challenges, such as the learning curve that came with understanding a complex biomedical device such as a ventilator and having to come up with new ways to improvise due to slow vendor response during the pandemic. A few of the biggest lessons we learned as a team include the importance of team dynamics, where each team member possessed a unique skill set but was still able to apply themselves to multiple tasks throughout the project. Effective communication, where we learned that communicating as much as possible was important to keeping everyone up to date on individual progress. And last but not least, being accountable, taking responsibility for tasks to promote trustworthiness within the team.